Perfect. We should be live on YouTube now.
Yes.
Wonderful. So let me share the screen, and if you have any question, guys, kindly write it in a Q&A, or you can just, contact the panelists, and they will tell me if there is any questions. So, okay. So during the last lecture, I'm not reviewing, but I will just go to the point that, what we got was a very important equation, which was we got Laplacian of the potential that we had. Of course, remember that this potential was a function of x, y, and z, and we got these to be equal to minus 4 pi delta of we say that is three-dimensional delta, but was delta of x. So I will come back to these, but that was a very important equation that we got, that we obtained. Okay. And we say, what is the delta function? And we say that, okay, loosely defining it is that when, let's go with the one-dimensional for simplicity, because we say if you have delta of x minus x0, so when x is equal to x0, well, is not equal to 0, that is a 0. When is x equal to x0, then, well, is roughly speaking is infinity, but that's not the only property. And the property that is completing it is that delta of x minus x0, delta of dx from on over all space, that is equal to 1. Or we can say that over this over a space that includes x0. Fantastic. And the definition was that, well, everywhere this function is 0 except one single point, which x is equal to x0. And here, what is the value is infinity. But if you take the Riemann integral, which is the integral of delta x on infinitesimal regions, then if you sum them up together, you will get 1. Where this is important, when the delta function is important. So assuming that I'm a boxer, and suddenly I punch on the face of someone, or I'm kicking on an object. Okay, so you imply a huge force on a short time. Of course, if you consider that I have an object and I apply this huge force, what is expected? I mean, you expected that you change the state of that object. So indeed, what you will do, you will apply a momentum to the object. So the object starts, if you assume that, well, I don't know, maybe saying that you have a bullet coming in, which is a huge force, is coming. I mean, suddenly you shoot on a wood, which if that is a mass of m, and that's a mass of m, and suddenly you apply this huge force, and then what you will see that this one is moving in that direction. Okay, when you can consider that is moving in that specific direction with the velocity of move. So for such kind of cases, when you have a huge force that applies in an extremely short time, you can say, well, if you write the force function, force is function of the time. Before the time of event, which I call it the time of t0, the force is 0. Before the time of, after the time of t0, also this force is 0. Okay, assuming that my hand is punching on something. So before the punch happens, essentially the force on this object is essentially 0. After that, also the force is 0 because I brought my hand back, but only in a very, very short time of, let's say, delta theta or delta tau, which happens at exactly at the time of t0. The force that I apply to this object is given by, let's say, F0. Okay. So and now I'm asking, how can I write this force in terms of mathematical equation, because always is difficult to handle all of these. While if you write a function which has satisfied these properties, it will be way easier to introduce it. Okay, so I will tell you that this function indeed ft is given by definitely delta of t minus t0, right? So why I write it in terms of delta t minus t0? Because that function is 0 whenever t is not equal to 0. But when t is equal to 0, t equal to t0, then that will be infinity. So I will call it p0. And I know that integral of f, let's not go with the vectorial equation, integral of ft dt, what it should be the value? Can you write it in Q&A? Yeah. So Baran wrote it properly. Is the momentum. So indeed, if you remember, F was given by dp dt, and from here you can calculate the dp is equal to f dt, and therefore the change in momentum, or let's say p minus p0, is equal to integral of f dt from time of, let's say, time of t1, time of t2, then you have a p1 and p2. Okay. So, and now, indeed, what we have, I introduced the force to be given in terms of the delta function, and this force is given by p0 delta of t minus t0. And for sure, integral of f t dt is equal to p0, the momentum that the object received. Will receive. Okay, so well, this is one way that someone can express an impact on an object with only the delta function. It's not the only way. I mean, these are in classical dynamics that people they use this, and by the way, it simplifies everything. It simplifies a lot of equations, and it gives you a huge help in doing the calculation. Other thing that people they care is going to be, I don't want to go deep into that form, which is a green function, but for the time being, I will say that is a charge distribution. Okay, charge distribution. And when I say charge, I mean electric charge distribution. Assuming that I have in the three-dimensional space of x, y, and z, I place a charge here in the place of R0. And the charge here is Q, let's call it R1. I will place the charge of Q1. And here in this place, R2, I place the charge of Q2. And now the question that I have is that what is happening with the charge distribution? If you want to write the charge distribution, charge density, of course, everywhere is zero. Everywhere is zero, except 2 points. Except point of R1 and point of R2, which at those 2 points, total charge is equal to Q1 and Q2. How can we write such a function? So rho of R can be written as Q1 delta of R minus R1. That means that the charge distribution, charge density distribution is zero except R1. And when you integrate of the total charges, the volume and the volume, that will be equal to integral of Q1 delta of R minus R1. Then I get Q1, dV, then I will get Q1, because the Q1 will be out of the integral, and integral of delta of R minus R1 on the entire the volume, that will be 3 integrals of delta function, that will be delta of x minus x1 dx, integral of delta of x y minus y1 dy, and integral of delta of z minus z1 dz. Okay, so, and then when you do the integral of all of them, then you will get 1, you will get 1, and you will get 1, and finally you will get the total charge. However, if you have 2 charges like the form that I have written here, then the charge distribution indeed is given by rho R Q1 delta of R minus R1 plus Q2 delta of R minus R2. And even if you have a third charge here, Q3, exactly what you will have a Q3 delta of R minus R3, and etc. Those are the point charges, by the way. And finally, I can say that that will be, if you have n charges, then you will have a Qi delta of R minus Ri when I is changing from 1 to n. You have n point charges of Q1 until Qn. So that will be the charge density, essentially, that you are describing for such a distribution of charges there. And finally, if someone is asking you, well, what is happening if I have such a kind of charge distribution? What happened with the potential? Can you calculate the scalar potential for this charge distribution? Then the scalar potential indeed is given by let's say at the point of R, if you want to calculate it, then that will be equal to 1 divided by 4 pi epsilon naught integral of charge distribution of R dr. Okay, or let's say R prime, just to be careful. And then from here, you can do the calculation, and what you will get 1 divided by 4 pi epsilon naught into summation of Qi divided by, of course, there is an R minus R prime here. and then you will get divided by R minus Ri. Good. So that's the way that we do the calculation, and we find the potential, and from the potential easily you can take the gradient of the potential with a minus sign, then you will get electric field, and then you have to take the derivative of the scalar potential, and you will get the electric field in the electrostatic regime. Well, lovely. So far, I'm now I can use the delta function, and I can I can describe physics for myself, or describe physics for specific problem that I'm dealing with. Remember, the delta function is very important. So I will encourage you really to read about delta of x property. So finding out what's going on with the derivative of delta x. You know the integral. Finding out what is happening with the delta of gx. So when is a function of a specific function. What is happening with the Fourier expansions, Fourier expansion of the delta function. What else? The Fourier Laplace transformation is easy, so it's not a big deal. Try to expand them in terms of, if you go with the Fourier expansions, you can try to expand them in terms of orthogonal function, other orthogonal function. And you will see why the delta Dirac is important, and it shows up in the calculation. Good. If there is any question, please, can you kindly write it down?
I think there is two general questions regarding the course. Lawrence asked, what are the physics prerequisites to introduce it?
Oh, Lorentz gauge, yes. Okay, I have not introduced the Lorentz gauge, but well, I can tell you, yeah.
Yes, and Mandal is, will there be a doubt solving decision for assignment question? Is general question, is not related to our today lecture.
Yeah, I will leave that the last question to the panelists. So,
Yes.
Well, so far I want to make sure that people, they understand the Dirac, and then I will, by the way, I will go to the gauges in a few minutes. So far, just remember that where the delta of Dirac appears in the calculation, and if you recall, once I say that, well, if the divergence of E is 0 when there is no charge, distribution, then I have the divergence of E is equal to 0. And then we say that E for a point charge is given by Q divided by 4 pi epsilon naught, and then you have R divided by R power of 3, and that was for a point charge, which the charge was at the location origin. And then here, that was the distance that we calculated the electric field here. And for this specific example, I say that what is going on with the divergence of E, and we did the calculation, we got Q divided by 4 pi epsilon naught. If I recall well, that was 3 R power of 3, if I'm not wrong, minus 3 R power of minus 3. And I say that is equal to 0. And people, they were asking me, well, but I know that there is a charge here, and the charge was here. So why the divergence of E is equal to 0? And I say, well, I have to be careful, because that is valid when R is not equal to 0. When R is equal to 0, then divergence of E is not equal to 0. Okay? Why? Because 1 divided by 0 is undefined, minus 1 divided by 0 is undefined again. So then, if you do the calculation, indeed, the proper expression for the divergence of E will be equal to Q divided by, yes, Q divided by epsilon naught. There will be a 4 pi showing up in the calculation, goes away, and then that will be delta of R indeed. So that was the result that we were expecting. So because the charge distribution, indeed, this part is nothing more than rho of R for a point charge, which is located at the origin. So I have to be very careful with this expression. Okay. So in physics, going back again to Maxwell equations and knowing that, well, you have a delta functions in physics, it appears many times that you are dealing with two equations. Divergence of a vector is equal to 0. Is defined. I call it S, which is a source. And curl of a vector is also defined. So that result is a scalar, which is a function of coordinate. It can be a function of R. That's a vector, which is a function of R as well. Okay. But what happens in usually what we need to know is that in order to, you will see that almost in all part of the electrodynamics, we have these two equations appear for electric field or for magnetic field. And if you recall, for electric field, that was divergence of E, assuming is in vacuum, is rho divided by epsilon naught. And remember, rho was a function of coordinate divided by epsilon naught. And the curl of E was given by minus time derivative of B. And also for magnetic field, we had a divergence of B equal to 0, and curl of B was given by mu 0 J plus mu 0 epsilon 0 time derivative of E. And the question is that why we care only about divergence and a curl? Why again here divergence and a curl? Because indeed in EM field, in electromagnetism or electrodynamics, we care about E and B. Why? Because from the Lorentz force, we know that Q is the force is given by QE plus V cross B, which V is the velocity of the charge. And then I can find out what is going on with the force on a particle, and then I can find the trajectory, and I have almost everything about that. Okay. So, but going back to the question that I asked, why we always care about the divergence and about the curl? And recall that also we say that, well, we usually don't deal with E and B. What we deal with is a scalar potential of phi and vector potential of A. How do we define E and B from these equations, these two expressions? E is given by minus gradient of phi. We drive this, by the way, minus time derivative of A, and B was given by curl of A. Even we had discussion about that if A is unique or it is not. Okay, if you remember that we say that you can change A to any A plus gradient of a lambda. And we showed that, well, if you do that, a magnetic field will not change. But what is happening with the electric field? Well, it's an argument that we have to discuss it, and that goes back to the direction of the gauges that one of the students asked, or one of the attendees asked. So far, so good. So yeah. I will not go through the direction of the gauge at the moment, what I want to ask is a very deep question. Why I care about the divergence of E, why I care about the curl of E. Will a vector uniquely be defined by having the divergence and a curl? Or no, I need something more than that. Okay, so I will ask, or I will repeat my question again. By the way, we will discuss the gauge later. Okay, but now the question is that, will a vector, let's call it vector of V, be uniquely defined by having its divergence and curl on a space? That's the question. What do you think? You can type it in the Q&A. No, seems no. They say that there is a constant. Yes, by Helmholtz theorem. Well, I have to be careful, Amir Hossein. We will go with that. So okay, so I see that people, they have concern, and some people they are posing some properties that or equations or theorem that I have to consider. So when it comes to these kind of problems, usually what we say, well, we say that let's prove it by contradictions. Okay, we assume, and that's a proof, we assume that no, there is another vector with the same property, the same feature. What are those features? I call it the vector of V prime. Okay, V prime is not a derivative, by the way, guys. Well, let's call it V1, which the divergence of V1 is S is the same, and curl of V1 also is the same. V1 has the same property, has the same properties. Good. Now I will consider a new vector of W. This is the definition, that this vector is V minus V1, is the vector that originally I had it here, and is the vector of V1, which I assume that is different from V. Now the question is that, what is happening with the divergence of W? What is the divergence of W? Can you write it down here for me? Well, some people, they are saying that is 0. So they say is a divergence of V minus V1, which is a divergence of V minus divergence of V1. What is the divergence of V? Is 0? Sorry, it's my apologies. Is SR minus divergence of V1 is exactly the same because it should be having the same property, so is equal to 0. So divergence of W is 0. Okay. So this new vector of W has a divergence which is equal to 0. What is happening with the curl of W? Is a curl of V minus V1, and that is equal to curl of V minus curl of V1, and again that is equal to S of R minus C of R and C of R, which is equal to 0. So curl of W also is equal to 0. Remember, we assume that V1 is different from V. We assume that there are two vectors. They have exactly the same physical properties, okay? But what we realize that the difference of the vector has the following property, which the curl is 0 and the divergence is equal to 0, okay? Wonderful. Now the question is that don't forget about V and V1, okay? We will discuss about this. Now I'm talking only about W. Divergence of W is equal to 0. What does it mean? W can be given by a curl of a vector. Curl of W is equal to 0. What do you will get from this? Can I write that W is given by gradient of a scalar? Do you agree? There is no need to have a minus sign, but if you want, you can add a minus sign. It's up to you, really. But the minus sign, as I say, is a convention that we say that water falls. I mean, the water goes down from a height. From mountains to the sea, not otherwise. So since the curl of W is equal to 0, then I can write W as being a gradient of a scalar quantity, which I call it W. I call it phi. Now, if you recall from the Gauss theorem, I say what is happening with the divergence of F gradient of G. Do you remember that? We proved that the divergence of F gradient of G, if you expand it, then that will be equal to divergence, gradient of F dot gradient of G plus F Laplacian of G. Okay? And from here, what I will get if I set, let us set F to be equal to G. So I can write it divergence of F gradient of F. Then what I will get here, I will get gradient of F power of 2 plus F Laplacian of F. Good? I think we are okay. Now, from these properties that I have, which remember we got that from Gauss theorem. We multiplied both sides by d tau, and we integrated. So it was integral of divergence of F gradient of F d tau is equal to integral of gradient of F power of 2 plus F Laplacian of F d tau. And this integral was on volume of V. This integral was on volume of V. We bring this integral from the volume to the surface. I will get integral of F gradient of F dot d sigma. is equal to integral of Laplacian of f power of 2, sorry, the gradient of f power of 2 plus integral of f Laplacian of f d term. So that was the equation that we had. That's on the volume, that's on the volume. This one is on the surface that the volume is created with, okay? So remember these integral. Now going back to here. So far, what we assume that we have a vector of v, which the divergence is clear, curl of v also is given, and we say that this v is not uniquely defined because I can find another v1 which has the same property. The divergence is given in a certain way. So then from these, I determine that you can get another vector which is given by the subtraction of these two vectors of v minus v1. And definitely we assume that v1 is different from v, so means that this w is not 0. Okay, is very, very important in my assumption because v1 is different from v. So, and we did the mathematics, and what we realized that, well, good divergence of v is 0, curl of v is given by 0. So then when the curl is equal to 0, then I will get w to be equal to a gradient of a scalar quantity. Then I can substitute it inside of divergence of w, and what I will get divergence of gradient of phi, which is equal to 0. That is coming from the first equation. Then this means that I have Laplacian of phi is equal to 0. Wonderful. Okay. So now I will use the Gauss theorem, which I have it here, right? And I say that let's write down this integral for a volume. This is the volume that I have W in, which this W has the following property. Inside of this volume, the divergence of W is equal to 0, and curl of W is also equal to 0. And that's a volume of V, and that's a surface, which is given by derivative of V. And writing the Gauss integral, I will write it for, instead of f, I will write it for a function of phi, is the same, that's a general statement. So integral on the surface of V is given by phi, gradient of phi dot d sigma is equal to integral of gradient of phi power of 2 d tau plus integral of f, phi Laplacian of phi d tau, and that's on the volume of V, that's on the volume of V. Good. What is the gradient of phi, guys? Can you write it down? I will scroll it down. What is the gradient of phi here? Do you remember? Is that one? Is W. We just got it here, right? What is Laplacian of phi? Laplacian of phi, we got it from this equation. What's that? Is 0. So that is equal to 0. Then what I will get here, I will get integral of magnitude of W power of 2 d tau is equal to, on the volume of V, is given by integral of phi divergence of phi d sigma. And if you remember, I say that the d sigma, which is element on the surface, is given by normal to the surface, which is this normal, dA. So then I can write it as a dA. So therefore, that will be integral on the surface of phi, divergence of phi dot n dA is equal to integral of W power of 2 d tau, and that's on a volume surface. So what is that, guys? Is the magnitude of a vector, okay? The magnitude is a scalar quantity on a volume. It tells me what is happening with every point that I have, the magnitude of the vector, and then you sum them up. So that will be summation of magnitude of W square on all points of the volume. It's essentially will give me the summation of all W's there. What is happening on the left side? What is happening on this equation? It seems that this summation of a vector W square modulus will be determined not on a volume, but on the surface. And it will be determined by two quantities. And remember, what is this phi? Is on the surface, which is on the boundary. What is going on with this is exactly the same. What is gradient of phi? What is this vector? Is W, right? So that will be W dot n, which I will call it Wn, which is normal of the vector W on the surface. So exactly, moving. So you got it properly. What is happening that this magnitude of the vector, which is W power of 2 on a volume, will be determined by the normal of the vector on a surface and phi. Okay, what is phi? Is the derivative of is the integral of the W, because I mean, what is the relation of phi and W is that W is given by a gradient of phi. So what we need this value as well. So we need phi. So coming back to the basic question, will a vector be uniquely defined only by having these two equations, divergence of V and curl of V, to be equal to S and C? Will they be uniquely defined? Most of you say no, which you are totally right, because if I go here, I will see that the difference of the vector, which is W, indeed is following the following equation. So it will not tell me anything about the uniqueness of V. So because I can build up another function which is different from V, and still it satisfies this equation. I have absolutely not a problem, no problem there. How can I make it to be uniquely defined? Now let's make it uniquely defined. So what was the condition? Divergence of V was equal to S of R. Curl of V was given by C of R. And now I will tell you exactly, is a boundary condition. I will tell you that in addition to this equation, we need to know V, or the value of V, on the boundary. Okay. Well, is one of the choices. I'm not saying all choices. So I will say that, well, Vn, what does it mean? Is the V dot n normal of the vector on the surface of boundary or on the boundary is known to me, is known to us. Lovely. So I know that what is going on with the Vn, okay? Normal of the vector on the surface. Lovely. And now I assume that, well, there is another function. There is another vector which has exactly the same property. What does it mean? That divergence of V1 is equal to S of R, divergence of, curl of V1 is equal to C of R. And then V1 dot n is known on the surface, and also it must be equal to Vn, means that V1 dot n is equal to, I don't know, a function, I will call it, I don't know, a function of g of r, and this is identical to the other vectors that we define it, which is Vn. Do you agree on that? Okay.
Dr. Ibrahim, I apologize for interrupt you,
No worries.
but we have a question.
Oh, I will answer the question in a few minutes.
Okay.
Don't worry.
Okay.
Yeah,
Sorry.
it will be exactly now.
Okay.
So now I assume that I have W, which is given by V minus V1, the same approach that we had it previously. So it means that the divergence of W is equal to 0, as we discussed. Curl of W also is equal to 0. So it means that from here, I will get W to be given by gradient of phi. And if you substitute it in this equation, I will get Laplacian of phi is equal to 0. Then I can use the Gauss theorem and I will get exactly the same expression. But in addition, what is happening? What is W on boundary, on the boundary? Or explicitly, if I want to say, what is happening with the W dot n on the surface, on the boundary? Can you tell me, guys? W is given by V minus V1 dot n. What is V1, V dot n minus V1 dot n? On the surface, it is exactly equal to 0. So now I will use the Gauss theorem that we previously had it here, right? That's the Gauss theorem. Now I will write it down. I have integral of phi W dot n dA on the surface is equal to integral of W power of 2 d tau, that is on the volume of V. So now the question is that previously we could not define it uniquely, but now what is the W dot n on the surface? On the surface, what is this value? We just showed that this is equal to 0. So it means that integral of W power of 2 d tau is equal to 0 for any volume of V that we consider. So for any volume, the absolute value of the vector magnitude on a volume is equal to 0. What does it mean? That W magnitude is equal to 0 because that is a positive value. It cannot be negative. On a volume, again, is a positive quantity. So what you expect, that W is equal to 0. So if the magnitude of W is equal to 0, then means that V minus V1 is equal to 0. Then means that V is equal to V1. So means that the two vectors, they are identical. So we say that they are different, but now you will see that if they have the same boundary condition, okay? If they have exactly the same boundary condition and the same expression here, then definitely these two vectors, they need to be equal to, they need to be identical. Oh, why we did say that W dot n is equal to 0? Because if you look at this expression, okay? What is the W dot n? Is V minus V1 dot n, right? What is V1 dot n on the surface? Is the same function as V1 and V2 for V and V1. Then that is equal to G of R on the boundary, minus GR on the boundary. That's a reason. No, dA is not a vector, remember. D sigma is a vector. D sigma is a vector of the surface, or the element of the surface. And usually we write it as n is the unit vector, which is changing, of course, the direction that multiplied by the magnitude. Okay. Any questions?
I think still,
yeah,
I think still we have.
Yeah, please.
I think still we have a question.
Yes.
Shaho asked the boundary questions for V1 and V1 are the same by assumption?
No, they are not the same by assumption. What we say, well, divergence of V is equal to S. Curl of V is equal to C, okay? And in addition to this, what we need to know what is V, I mean, the derivative of V with respect to N, or V dot N on the surface, okay? We know that V dot N on the surface is given to us. This is what I'm spending a lot of time to just tell you. Then I say, in addition to this, I assume that I have another function which is satisfying exactly the same property. What are those same property? Is the divergence of V is equal to S. So divergence of V1 also is equal to S. Is exactly the same function. Curl of V1 also is the same function, which is C vector. And V1 also on the boundary is exactly the same function. So it means that if V dot n is equal to G, definitely V1 dot n also is equal to G. It's not by assumption, because it should be exactly satisfying the same boundary condition. That's the reason that W on the surface will be equal to 0. Normal of W on the surface is equal to 0. Okay.
Okay. So still we have another question, and this question from previous from the integral equality. Where does it follow from the V? It is not the unique. I don't know. I think he asked some previous from the previous. slides, I think.
Um,
I don't know what it does mean.
can you elaborate further on this question? I mean, I'm asking the person that asked this question.
Yeah, I hope so.
Okay.
Okay, thank you. Yes.
So we can follow.
Thank you. Yes.
Okay, lovely. Now, apart from saying, well, okay, now that's a reason that Maxwell equations by itself, they are not uniquely determining electric field and magnetic field. But what we need in addition to Maxwell equation is boundary condition. What is happening with the vector of V on the surface? Okay. V dot n should be known on the surface. Of course, there is another way. Look at this integral that we had here. Okay. Two things, they show up on the surface. One is integral of phi w dot n dA, and the other side is, of course, is w magnitude power of 2 d tau, and that's on a volume of V, and that's on a surface. Remember, that's on a surface, which is what we call it the boundary. Okay, so so far we talk about what is going on with the value of W, which means that the value of V on the surface. But there is another way that we can think of that, which is what is happening with the value of phi. What is the value of phi? Phi means that the gradient of phi is equal to W. So what we need the value of the scalar potential, scalar function on the surface, and I'm giving you a hint because that is very important, and that goes to the direction of the Green's theorem, and indeed going to the direction of the, either you will have Dirichlet boundary condition and you have a Neumann boundary condition. Well, we will discuss that later on. Do you remember the Gauss theorem? I mean, we say that the divergence of F gradient of G is equal to F dot G minus plus F Laplacian of G. And in the same fashion, we can write down what is going on with the divergence of G gradient of F. So that was gradient of G, that gradient of F plus G Laplacian of F. And we say that subtract these two together, what you will get the divergence of F gradient of G minus divergence of G gradient of F equal to Papa F Laplacian of G minus G Laplacian of F. And then when you integrate this, you will get integral. I will go with the Gauss theorem, and then I will get F gradient of G minus G gradient of F on the surface, d sigma. Remember, d sigma is n that dA on the surface is equal to integral of F Laplacian of G minus G Laplacian of F on the volume of d tau, and that's on the volume of V.
Professor, I'm aware that there's a question that the Rupesh-Dinesh Mandal, can you answer it right now?
Oh, yes, sure.
He says that is it possible to take infinitesimal length at the boundary of any space, and how we decide that would be a boundary of that particular surface?
Is it possible to take infinitesimal length at the boundary of any space? And how we decided what would be the boundary of that particular surface? We did not decide any. Well, let's review. So I have a boundary condition, and I assume that this is a three-dimensional space. Is a three-dimensional space. Okay. So that is a surface of let's call it S. What is happening inside of this? Divergence of V is S. Curl of V is equal to C. And what is happening with the V on the surface? I'm not talking about infinitesimal V. I say that what is happening with the V on the surface, at the surface, definitely dot N is given. Okay. That is what I'm assuming. You can take an infinitesimal, let's say, surface here, and then that will be N, and that will be dA. And then even you can define for these infinitesimal what is happening with the V value. And V dot N in any cases is a function for that local point, which I will talk about that. So is local point of R0, okay, which is given by R0. That's it. I have not assumed any strange, let's say, assumptions in there. What I'm saying that, well, on the boundary, I will see that that is changing. So, for example, if you assume a sphere as a boundary condition, I will say that, well, if you assume that is a theta function, if that angle is theta, then electric field is depending on the theta. So, electric field will be given by, maybe has meaning or not. It will be given by R on the surface. A constant value of A. That is one possibility. Or I can tell you that is given by cosine of or. So then E at the boundary, on the boundary, is constant, is A, is a fixed quantity. While I can assume another boundary condition, which is E on the boundary, E on dot R is cosine of theta, which this theta is this angle. There's another possibility that I will give it to you on the boundary. So what does it mean that, for example, if here is theta equal to pi divided by 2, cosine of pi divided by 2, that will be equal to 0. So it means that here there is no electric field. While if you go to the other direction, the electric field will be negative. So that's the boundary condition that I can have it.
I think he answered.
Okay, perfect. Fantastic.
Thank you.
So now let's go to another example, which is very very important one, and this example is going to be the what we call it the Helmholtz theorem, or second Helmholtz theorem, and is really important one. So far, we say that Maxwell equations, if you have Maxwell equation with a proper boundary condition, then we can easily say that this function is uniquely defined. Okay, so we have absolutely not a problem. So we need Maxwell equations and we need boundary conditions. Then it's okay. We are perfectly fine. Now the second part is important. We say, okay, we know that will be the that function will be uniquely defined. But what is the value? Now, the second question that I'm asking, what is the vector V? Remember, that's a follow-up question of the previous example that we had. So means that the divergence of V is equal to S curl of V on specific volume is given by C, which both of them, they are function of R, by the way, remember that. If they are not constant, is a general function, and V dot N on the boundary is given. Okay. Now the question is that what is the vector V? Okay, and remember that's on a volume. So that's what we call it, the second part of Helmholtz theorem. Helmholtz theorem says that, well, definitely V can be given by a gradient of a scalar. Let's put a minus sign for the convention, plus curl of a vector. Okay, that is the that's the assumption, and that's what Helmholtz theorem will tell us. So if V is uniquely defined, then now this V vector is given by a gradient and a curl. Well, it's again, it looks like a loop that you go from the divergence to divergence of a curl and a curl. You say that this is uniquely defined, but now is given by a gradient and also a curl. Remember, that's a normal vector. And that's a tangent vector. Okay. Let's see if that is true. So, well, I say fantastic, but what is happening? Of course, you can say that this is true, but what is phi and what is A? How can I find the phi and A? Well, I would say that replace it inside of the divergence of V. Then means that the divergence of minus gradient of phi plus divergence of curl of A, which is equal to, what is the divergence of a gradient? It will be Laplacian of phi. Divergence of a curl, guys? Exactly. Is 0. So we calculated the divergence of V, which is given by minus Laplacian of phi. And what is the divergence of V? Is equal to S. So S of R. So from here, I will see that the Laplacian of phi is equal to minus S of R. If that is true, if I can write V in terms of gradient or minus gradient of phi plus curl of A, then the divergence of V will tell me what is happening with the Laplacian of phi equal to minus S. What is happening with the curl of V? Curl of V means that you have a curl of minus gradient of phi, right? Plus curl of A. Curl of a gradient, zero, perfect. And then the second term that will be 0, because that is a curl of minus gradient of phi, which is equal to 0. And then the second term will be curl of A. I can use the backup rule, and then what I will get from here, I will get a gradient of divergence of A minus Laplacian of A. True, guys? That's good. So myself, I will choose, well, the divergence of A to be equal to 0 because it's a freedom that I have. You remember that, so we say that A can be changed in such a way that A plus gradient of lambda will be invariant. So that's a choice that I have chosen, and it's going to be the gauge problem. So we assume that divergence of A is equal to 0. Then what I will get from here, I will get exactly the same expression. Laplacian of A is equal to minus C of R. Okay. Good. Perfect. That's the one choice, by the way. It's not all choices that we have. So, but we can change it later on. I will restrict myself to the first choice, and I will give the second choice as an example to yourself to prove it. So now what I have, Laplacian of phi is equal to minus S of R. Okay. Where did I obtain this? I obtained this from the fact that V is given by minus gradient of phi plus curl of A. And divergence of V is equal to S of R. Okay, so from these two, I obtained this equation. Remember why I'm doing that. The uniqueness is defined, absolutely not a problem. Now the problem is that how to find V. And we say that V is given in two terms. One is a gradient of a scalar, and a curl, or the other term is a curl of a vector. And now the question is that how to define phi, how to get phi, and how to get A. So those are the problems that I'm looking for right now. So, and I substitute it, and then I will get this equation, which is an equation will tell me what is the expression of phi, this phi, which I have to substitute it there, in terms of the source function. Lovely. No question? I see one. Can we use Helmholtz theorem to write Maxwell equations? No. What do you mean by writing the Maxwell equations? Helmholtz theorem, there are proofs to say to you that a vector in a volume and based on a boundary condition will be uniquely defined, and what will be the values of them. But you cannot, why you are writing the divergence of E is equal to rho divided by epsilon naught. Those are Maxwell equations that I call them. Okay, you cannot go in this way. So if Laplacian of phi is equal to minus S, which I obtained from the theorem that we discussed, now I want to find what is going on with the phi. I want to find out what is phi. Good. Let's review the gauge theorem that we had. And the gauge theorem that we had was integral of, on the surface of f gradient of g minus g gradient of f dot n dot dA. That was a d sigma, remember? On the integral of volume of f Laplacian of g minus g Laplacian of f on a volume of v dv. Good. Now I say, well, I consider two functions, and these functions, one of them is phi, which Laplacian of phi is given by minus s of r. Okay? Is important to remember that. Now I will assume another function, which is, this function is 1 divided by r. Later on, you will see that it has a certain name. Let's assume this function. I have one function of phi, and I have this function. What is happening with the Laplacian of 1 divided by r? What is Laplacian of 1 divided by r? Do you remember that? Was minus 4 pi delta of r. Exactly. I mean, Hossein said perfectly. Lovely. So I will call this one f. I will call this one g. And now let's substitute it inside of the Gauss theorem that I had. So that will be integral of f, which is phi, g, which is gradient of 1 divided by r, minus g, which is 1 divided by r, gradient of f, which is gradient of phi, dot n dA, that is on a surface, equal to integral of f, which is phi, Laplacian of g, which is Laplacian of 1 divided by r, minus g, which is 1 divided by r, f, which is Laplacian of phi. dV. Okay, that's on a volume. Oh, you say dV or d12? Yes, dV is fine. Now I will simplify this. The right side, the left side, well, let's keep it at this moment like that. So gradient of 1 divided by r. Do you remember that? You write it down for me. Minus r divided by r power of 3. Okay. Minus 1 divided by r. Gradient of phi dot n dA is equal to integral of phi. Laplacian of 1 divided by r is minus 4 pi delta of r. And finally, I have 1 divided by r. Laplacian of phi, which is Laplacian of phi, is minus s. So it will be plus s of r dV. And that's on a volume. Wonderful. Remember, gradient is not a scalar quantity. Gradient of 1 divided by r will be r hat divided by r power of 2, which is exactly the way that one of the attendees mentioned that. So good. So let's simplify this. What is happening with the first term? The first term is minus 4 pi integral of phi, which is a function of r, delta of r dV. And the second term is plus integral of s of r dV divided by r. That's on a volume. That's on a volume. What is the first integral, guys? Exactly. Integral of delta function, right? If you remember, we say integral of f of x, delta of x minus x0 dx on all space is equal to f of x0, is exactly phi of 0, right? So that's the potential, that's what we call it, the scalar potential at that point. What is happening with the left side? So let's write it down. So I will keep that side here, which is minus 4 pi phi of 0. I will bring it to the left side, and I will take the left side to the right side, and I will write it down. So it will be phi of 0, potential at the 0, or potential at the origin, is equal to 1 divided by 4 pi, because it becomes plus sign, and 1 divided by 4 pi of, I have two terms. The first, three terms. The first term is 1 s of r divided by r dv, and the second term will be minus sign of 1 divided by 4 pi. Then I have integral of, the first term will be phi the minus sign goes away. I will write it as a plus, so it will be phi r dot n divided by r power of 3. The second term will be 1 divided by r gradient of phi dot n dA. That's on the surface, and that's on the volume. So V was given by two terms. We had two terms. The first term was minus gradient of phi, and the second term was a curl of A. This phi is given by this equation. So indeed, this phi is given by S, which is coming from the divergence of V equal to S. And then it comes back to also the value of phi on the boundary. That's a phi on the boundary. Or what you need also the gradient of phi dot n on the boundary, which means that also it comes from the fact that what is going on with the normal of the vector v1. So indeed, you have two choices to determine the phi on the in general. Either you know what is happening with the potential that you have it here on the boundary is one choice, or the second choice that you have it, what is happening with the normal to the vector, which is phi gradient of phi dot n on the surface. If you know these two, or either on the boundary, then your potential is perfectly defined in the volume of V, which we consider. That's really an important rule, and this is what we call it the boundary condition issues. And the first scenario, as I say, is the Dirichlet boundary condition, and the second scenario is what we call it the Neumann boundary condition. You can have a mix of the two. For one part of the region, you have a derivative, or for other part, you have the phi indeed. So this is what we call it also the mixed boundary condition. And then to have the electrodynamics, the first 3-4 chapters of Jackson is about this, handling how to work with the boundary condition issues. In a similar fashion, I will encourage you, in a similar fashion, do the calculation for the Laplacian of A equal to minus C. That's a three-dimensional Laplacian. So it's a vector in a vector Laplacian, and you have to solve it, and exactly you will get the same expression. Is there any question, by the way?
I see no questions right now, Professor.
Lovely. So now we completed the vector analysis, and remember again, the entire of these vector analysis are very, very important for electrodynamics. We started with a scalar quantity. We defined what is a scalar quantity, which upon rotation does not change. Then we defined what is going on with a vector. Then we went from a vector and we built up a scalar quantity, and we built up what we call it a pseudo vector, which will be defining it in the next two lectures. And then we introduced the dot product, the cross product. We introduced the gradient, which you can bring a scalar to a vector space. And we introduced the divergence, which is taking a vector and bringing it out to a scalar quantity. And also we introduced the curve. We talked about the physical meaning of all of them. We try to use them in electrodynamics, and we drive the wave equation indeed. And finally, we went with the case of the delta Dirac, which is extremely useful to describe the distribution of the point charges or impacts. And finally, we say that why we care about all of them, because they can be uniquely determining a function in a space, a vector function in a space, if you give the proper boundary condition. And we say, what are the form of them? They are given these following forms that people use it. For example, if you remember, the divergence of E is given by rho divided by epsilon 0, right? Explicitly is look like that. So what I have to do, the potential that I will obtain at the origin is 1 divided by 4 pi, and S that I have here is given by rho divided by epsilon naught dV divided by R, plus the boundary condition, which is, it should be determined, and that is given by 1 divided by 4 pi epsilon naught integral of rho dV divided by R. And this is the form that we use it. We use it in electrostatic. Isa, by the way, some people, they say that they had terrible internet today. So I expect more that will happen. Go to the YouTube channel and that will be uploaded automatically. Okay. Well, if there is no question, in the next half an hour, I will go from Cartesian coordinates. Slowly, I'm preparing you to the tensor calculation. We will go from the Cartesian coordinate to other coordinates, which they are important. So far, if you look at the Cartesian coordinate, in Cartesian coordinates of x, y, and z, indeed, what we have 3 vectors, as we say, or 3 axes, and these 3 axes, x, y, and z, indeed, they are built up based on the knowledge that we know the x value for a point. So it means that I will make a plane like this on a certain x value of x0. Then you know a y value, so I will call it y0, and I will make a plane which is determining the y value. Okay. And finally, I know a certain z value, which this z value indeed is given, for example, here, z0. Oh, let's go upper. Sorry, maybe it's better to go upper. Let's say this is the z0. And then you determine a point of z0. So in the intersection of all these 3 planes, you will find out a point, which this point is given by x0, y0, and z0. So you uniquely define that point. Lovely. Why we love Cartesian coordinates? because in the direction of x, we have x hat. In the direction of y, we have a y hat. In the direction of z, we have a z hat, which the magnitude of them, x1, y hat also is 1, and z hat is 1. And moreover, the directions are fixed. They are not changing in space. So x hat, y hat, z hat, which they form a right angle. This is the same x hat, y hat, z hat if you move it here. Okay? Is fixed and has absolutely no problem. And that's a uniqueness of the Cartesian coordinate, which we love it very much. However, that is not true for any unique vector. For example, you can have in two-dimensional space, right? In the two-dimensional space of x, y, and then I go to the polar coordinates. What is the polar coordinate? Well, any point here is determined by a distance, which I call it rho, and an angle, which I call it phi or theta, is up to you. Okay? Do you agree? And the relation between x and y is x, y, and rho and theta is that. So x is given by rho cosine of theta, y is given by rho sine of theta. Or if you go otherwise, or if you want to look at the relation of rho and the x and y, it will be x squared y squared, and theta is given by arctan of y divided by x. Okay, rho is changing from 0 to infinity, and theta is changing from 0 to 2 pi. Okay, and here x is changing from minus infinity to plus infinity, and y is changing from minus infinity to plus infinity. Okay, but now remember, what is x hat is like that. What is y hat is like that. But what is rho hat? Rho hat is like this. It's a unit vector of rho, which means that the magnitude is equal to 1. But what is rho hat in this point? It's like this. What is rho hat here is like that. What is theta hat like that? Theta hat will be like this. And here is like this. And you will have a lot of problems then, because rho hat and theta hat, I mean, the unit vectors of polar coordinates, indeed are coordinates function. What does it mean? That is true that the magnitude of rho is equal to 1 and magnitude of theta is equal to 1, but rho indeed is a function of either I can write it in x and y, or you can write it as a function of rho and theta. And theta in general, of course, it's one single value, and theta also is a function of rho and theta. So when it comes back to these coordinates, and that, by the way, this is a general formalism, general. Explicitly in this specific case, they are function of theta, just to tell you. In this specific case, they are only function of theta. They are not function of the distance. Lovely. So now you understand why this is important. The importance is that, well, the Cartesian is a special case when everything is beautiful, but it happens that, well, some physics can be easily solved based on a symmetry in the different coordinates, which, for example, someone, if he's working in optics and they want to solve wave equations, they prefer to solve the wave equation in cylindrical coordinate, because all optics that we have it in the laboratory, mainly they are cylindrical symmetry. Or someone, when, for example, working with black holes, so it's better to solve in a spherical coordinates. When someone is solving gravitational forces, it's better to solve it in spherical coordinates. Or, for example, if you have a wire of infinity, it's better to solve in a cylindrical coordinate, finding out what's going on with the charge distribution, and etc. So the coordinate is chosen based on the symmetry that you have, which simplifies the calculation way easier. So it may happen that in general, you may choose, or even you may introduce a new coordinate in order to solve a problem. And I call these coordinate based on certain parameters. I call them curvilinear coordinates. And the parameters in the three-dimensional way, I call them Q1, Q2, and Q3. Remember, they are parameters of your coordinates. What does it mean? Well, they look like X, Y, and Z in the three-dimensional fashion. I can introduce it also in n-dimensional, but we don't go there yet. So let's keep it for the three-dimensional way. For example, in cylindrical coordinate, that can be rho, theta, and phi. Cylindrical coordinate is Z. In spherical coordinate is R, phi, and theta. Okay. So it can be any values. But what does it mean if I have these coordinates of X? I always have the Cartesian as a background because I want to give you the feeling. So, for example, Q1 can be one parameter which defines, let's say, a certain phase, a certain, let's say, value. So I will call this Q1, and this is the Q1 constant. It look like the previous case that we say, these look like the X0 constant. And that was the green one was look like Y0 constant. And the orange one was look like a Z0 constant. Here, the same situation. I will say that while Q1, when Q1 is a constant, that can be a Q1, let's say 0, then you have a surface which is given like this, which is, by the way, a cylindrical coordinate. When we talk about, let's say, Q2 constant, then I'm talking about these, let's say, plane. Okay. Which means that I have the specific point in space. And the angle with this one is, I call it theta. And then when you talk about the Z point, or Q3 equal to a constant, I talk about only explicit distance of Z0. So this is the way that I will introduce these curvilinear coordinates. And I say that these are the three parameters that I'm dealing with. And these three parameters, they introduce three different planes of constant values. And they can be in general orthogonal to each other or cannot be orthogonal to each other. It can be a general formalism. So, but what indeed is clear, like the example that I previously said in the polar coordinate, that these rho theta z r phi theta, they can be explained in terms of, or they can be expressed in terms of x, y, and z. So indeed, these q1, q2, q3, they can be in general function of x, y, and z. Q2 also can be a function of x, y, and z. Why I'm doing that? Because I know how to handle Cartesian coordinate, but I want to do the generalization formalism. Q3 also is a function of x, y, and z. Okay? Any questions so far? We are okay?
Well, Professor, we have no question, but someone asked something from the technique of this course and asked whether can you introduce a covariant differential and geodesic as well?
Oh, yeah, we will do that. It's exactly the same direction that I'm going.
Thank you, Professor.
Of course. Do you have any questions so far? I mean, related to this topic, because I'm changing now from the Cartesian coordinate to any arbitrary coordinate of Q1, Q2, and Q3. And later on, I will go with the QI. I can extend it to n-dimensional space. Okay.
Well, I see no questions right now. I think we have not.
Beautiful, Ahmed. Thank you very much.
Thank you, Professor.
So then, these three new parameters of Q1, Q2, and Q3, they're a function of X, Y, and Z. And what I know, of course, that the same way, I can say also X is a function. I can invert the function, and I can say X is a function of Q1, Q2, and Q3. Y the same can be a function of Q1, Q2, and Q3. And Z as well. It can be function of Q1, Q2, and Q3. Remember, that's exactly look like this. I know that what is X in terms of rho and theta. Also, I knew what is rho in terms of X and Y. And theta as well in terms of X and Y. Okay, so here is exactly the same expression. You can write also X in terms of Q1, Q2, Q3, Y as well, and Z as well, and or in the reverse way, you can determine what is going on with Q1, Q2, Q3 in terms of function of X and Y and Z. Why I'm doing that? Because it's way easier for me to handle the Cartesian coordinate and generalize it. So let's do that. So assuming that, well, I'm in the Cartesian coordinate, what is the length? dr power of 2 is dx power of 2, dy power of 2 plus dz power of 2. Do you agree? Or I can even write it as perfect moving. So, or we can write it as a I dxi power of 2, which I is changing from 1 to 3. Lovely. We have this relation. So now let's do the calculation and find out what is dx. What I'm going to do, I want to write dr square, infinity small length or increment of the length in terms of Q1, Q2, Q3, infinity small displacement there. Okay. Remember, Q1, Q2, Q3, in general, they are parameters, not necessarily length. So you have to be very careful with that. So let's do the calculation and find out what is going on with dx. So dx means that, well, I have to calculate what is going on with the differential of q in dx, which is a function of q1, q2, and q3. Then I have to calculate the differential of that for increment of dx1, dq1, dq2, dq3. So I will go with the partial derivative of x with respect to q1, dq1 plus partial derivative of dx dq2 dx dq3. Agreed, guys? In the same way, perfect. In the same way, I can write down dy, which is again derivative of y with respect to q1 dq1, derivative of y with respect to q2 dq2, derivative of y with respect to q3 dq3, and the same way for dz, so which is derivative of z with respect to q1 dq1, derivative of z with respect to q2 dq2, plus derivative of z with respect to q3 dq3. Now I will be calculating what is going on with the increments of the length, which is dx power of 2, dy power of 2, plus dz power of 2. I have to make the power of all of them. So I will get this expression here, power of 2, this expression power of 2, the expression power of 4. So let's do that. And then what I will get derivative. I can simplify this. Let's write it down in a more simplified version. I will call it down k dxk, if you agree. This is exactly the same way. It looks like dx power of 2, right? So it's summation of k dxk power of 2, which is k changing from 1 to 3, is the same expression. And dx1 is equal to dx dy. So x1 is equal to x, x2 is equal to y, and x3 is equal to z. So, and then for the dxk, what I have a partial derivative of xk, derivative with respect to qi, dqi, and that's in the summation of I, is exactly the same expression as this one, or the other one, or this one is the same. So then I will have the summation on I, partial derivative of xk with qk, qi, dqi. That's the first dx. The second one is the same, but just the index should be a different index. So I will write it as a j, partial derivative of xk, qj, dqj. And remember, that's on a j, that's on a I, and that's in the summation on k. So if you simplify this, then you will get summation on a, summation on j, then I have dqi, dqj, and then I have the summation on k of partial derivative of xk with respect to qi, partial derivative of xk with respect to qj. So whatever is that is independent of k index, because I'm summing over the k. So the result of this is a function, it depends on I and j, and I call it gij. Gij, I will introduce it as a summation on k of partial derivative of xk with respect to qi, partial derivative of xk with respect to qj. Okay, and we call these the space metric. So indeed, dr power of 2 now is given as a summation on I and j of gij, dqi, dqj. Okay? Questions?
No, doctor, we have no questions.
Lovely.
I think someone said, yes, we have one question right now. From
Why?
Ivan.
Okay.
Why did you introduce the sum over the second index j instead keeping the single index I, and why j is above?
E1 is asking why did you introduce the sum over the second index I instead of keeping the index j? Oh, because, well, remember, you're talking about these expression. So we introduce, well, we say that let's write it in the compact form. I don't want to handle the three derivatives together. I write it I, but this, when it comes to the second term, which is the dk, well, it's true that it's the same, but if I introduce I here, this I will be mixed up with the other I here. Remember, you sum over the I here. You cannot introduce another I because this, you cannot clarify which summation is over which part. Okay, that's a reason that we have to write it in this way. If well, in our calculation, yes, we compare all of them with the Cartesian, but in these can be in general formalism. Okay, I mean, I was saying so. Yeah, it's a general formalism, but we started from the Cartesian coordinate because we understood very easily. But in general, no, you can introduce, for example, you can even build up your vector space based on special functions, and you can introduce a metric in that space. Okay, and not necessarily that you will go with a Cartesian coordinate. It can be also functions, as I say, is a vector space. So Gij, as I say, the metric now is defined as a summation on k, which k is changing from 1 to 3, partial derivative of xk, qi, xk, qj. Okay, so for example, G11, what is G11? Is a summation on k equal to 1 to 3 derivative of xk, derivative of xk with respect to q1, with respect to q1. And that is nothing more than derivative of x, q1 power of 2, derivative of y with respect to q1 power of 2, derivative of z with respect to q1 power of 2. That's a G11. As we say that I and j, they change from 1 to 3. So indeed, the metric has 3 by 3 components. That part is a G11, G22, G33, and that is G12, G13, and that is a G21, G23, sorry, 3, 2, G31. Okay, so you have the 3 and the 9 components, and essentially what you need, indeed, you only need 6 of them to be calculated because it's symmetric. I mean, Gij is equal to Gji. For well-behaved function, this is what we have. So essentially, this is what you will get. So it's the summation on k is a derivative of xk with respect to qi, derivative of xk with respect to qj, which is identical to the derivative of xk with respect to qj, derivative of xk with respect to qi. Okay, lovely. So any questions? So indeed, dr squared, you have the following term. Look at the term, it is very, very important. You have G11 dq1 dq1. So it's G11 dq1 power of 2. G12 dq1 dq2. G13 dq1 dq3. G21 dq2 dq1. G22 dq2 power of 2. G23 dq2 dq3. G31 dq3 dq1. G32 dq2, sorry, 3 dq2, and G33 dq3 power of 2. As I say that this one is identical to this one, and dq1 dq3 is equal to dq3 dq1. So indeed that can be simplified further. You can write it in this way: G11 dq1 power of 2, G22 dq2 power of 2, G33 dq3 power of 2, and then you have plus 2 G12 dq1 dq2 to G13 dq1 dq3 plus 2 G23 dq2 dq3. For I will tell you further, so you can calculate these metric as we said for orthogonal coordinates. This is a special case, by the way. It is not a general statement. For orthogonal coordinates means that Q1, Q2, and Q3, if you look at the constant plane of Q1, Q2, Q3, if they form orthogonal situation, then you will see Gij if I is not equal to j is equal to 0. Okay, so does it mean that dr square is indeed given by G11 dq1 power of 2, G22 dq2 power of 2, plus G33 dq3 power of 2. And that is for the case that you have orthogonal coordinates. And that will be the subject of some of the discussion that we will have. But in general, you may not have this condition. In general, you may work in a coordinate which Q1, Q2, and Q3, the constant plane of them, they are not orthogonal to each other, but they can means that the unit vector that you determine for them, they are not orthogonal to each other. Then the metric of the space has this term as well, these terms here as well. Not only the first one, the first set of the three, but also the last three sets as well. So you have to be very careful how to handle this. I will be stopping here, and the next lecture I will go with a few examples of how to drive this in a general formalism, and how to drive divergence, gradient, curl, and even going with the Laplacian in these coordinates. And finally, we will extend it to n-dimensional space, and we will go with the definition of the tensors and pseudotensors. Yeah, so I will stop here, and I will be open to